Hi, welcome you all. Today I am going to explain Cauchy's integral theorem, Cauchy's integral formula, generalized Cauchy's integral formula, and Liouville's theorem. First come to the Cauchy's integral theorem. Before going to Cauchy's integral theorem, we state the Green's theorem. Green's theorem is the theorem which gives the relation between line integral to double integration. Let's see the statement of the Green's theorem. If p of x comma y and q of x comma y be two continuous functions having continuous first order derivative in region R consisting of points within and on the simple closed contour C, then line integral over C capital P into dx plus q into dy is equals to double integral over R dou q divided by dou x minus dou p divided by dou y into dx dy. Here dou some are pronounced as a del. So del q by del x minus del p by del y, which is your convenient, that pronounce you can use. Okay, now come to the statement of the Cauchy's integral theorem. If a function f of z is analytic at all points within and on a closed control C, then integral over C f of z into dz equals 0. If our function is analytic within the contour C on a closed curve C, then that integral value over that closed interval C is always a 0. Let's see the proof of the Cauchy's integral theorem. Let our f of z is u plus I into v and dz equals dx plus I dy. Then the integral over C f of z dz is equals to integral over C u plus iv into dx plus I dy. Multiply these two complex factors, we get integral over C u dx minus v dy plus I times of integral over C v dx plus u dy. I consider it as a equation 1. By the data, f of z is analytic, hence it is differentiable, which implies that f dash of z exists and continuous in the region R on curve C. Also, f of z satisfies the CR equations dou u by dou x is equal to dou v by dou y and dou u by dou y is equals to minus dou v by dou x are satisfied. Observe a real part and imaginary part of equation 1. Real part u dx minus v dy, imaginary part integral over c v dx plus u dy are looks like a LHS of the Green's theorem condition, that is integral over c p dx plus q dy. Hence I apply the Green's theorem for real and imaginary part of the equation 1. Hence I get integral over c f of z dz is equals to double integral over r minus dou v by dou x minus dou u by dou y into dx dy plus I into double integral over r dou u by dou x minus dou v by dou y into dx dy. Now apply the CR equation for this equation. I get double integral over r dou v by dou x is nothing but dou u by dou y minus I retain dou u by dou y as it is into dx plus dx into dy plus I times of double integration over R, replace dou u by dou x by dou v by dou y by CR equation minus and retain dou v by dou y as the above into dx dy. Dou u by dou x minus dou u by dou y is nothing but 0 plus I times of dou v double integration over R dou v by dou y minus dou v by dou y is 0, hence the whole term become 0. Thus integral over c f of z into dz equals 0, hence the theorem. Now see some consequences of Cauchy's integral theorem. Under that, first one is, if f of z is analytic in the region R and if capital P and capital Q are any two points in it, then integral from point P to Q f of z into dz is independent of path joining the points P and Q. That implies that our function is analytic, then the integral is a path independent. Now come to the second consequence. If C1 and C2 are two simple closed curves such that C2 entirely within C1, and if f of z is analytic inside and on the boundary of annular region between C1 and C2, then integral over C1 f of z into dz is equals to integral over C2 f of z dz. That means if a two simple closed curves contain one another, then their integral values are same if our function f of z is analytic. Next theorem is Cauchy's integral formula. Statement of Cauchy's integral formula is, if f of z is analytic inside and on a simple closed curve capital C, and if A is any point within C, then f of A is equals to 1 divided by 2 pi I integral over C f of z divided by z minus a into dz. Now come to the proof. Since a is any point within a contour C, there is a circle C1 with z equals a as center and r as a radius such that C1 entirely within the C. So observe a diagram. This one is our closed contour C. This is our point A. We can construct a neighborhood around this point A, such as a circle around A with radius R and center A. So as f of z is analytic, we have f of z divided by z minus a is also a analytic inside and on the closed region capital C as well as C1. Hence we have integral over C f of z divided by z minus a into dz is equals to integral over C1 f of z divided by z minus a into dz. This is according to above consequence second. But equation of a curve C1 is a circle, that is mod z minus a is equals to r. That is nothing but z minus a is equals to r into e power I theta. This one also can be written as z equals a plus r into e power I theta. Here just I taken left hand side a to the right hand side, where theta is varies from 0 to 2 pi. Differentiate this with respect to z and theta, we get dz is equals to r I e power I theta into d theta. Thus, our integral value over c f of z divided by z minus a into dz is equals to integral from theta equals 0 to 2 pi f of z is nothing but a plus r into e power I theta, and z minus a value equals r e power I theta into dz value is r I e power I theta into d theta. On simplification, we get I times of integral from theta equals 0 to 2 pi f of a plus r into e power I theta d theta. Choose our r as very small, that means r as tends to 0. Thus we get integral over c f of z divided by z minus a into dz is equals to I into integral from 0 to 2 pi f of a into d theta. F of a is independent of theta taken outside. I into f of a, on integration of d theta we get theta from 0 to 2 pi. So final answer is 2 pi I into f of a, which implies that f of a equals 1 by 2 pi I into integral over c f of z divided by z minus a into dz. Here 2 pi I is taken to the denominator of LHS. We get a final formula. Now come to the generalized Cauchy's integral theorem. Statement: if f of z is analytic inside and on simple closed curve C, and if a is any point within C, then fn of a is equals to n factorial divided by 2 pi I into integral over c f of z divided by z minus a whole to the power n plus 1 into dz, where fn of a is the nth derivative of f of z. Now come to the proof. We have Cauchy integral formula, that is f of a equals 1 divided by 2 pi I into integral over c f of z divided by z minus a into dz. Applying the Leibniz rule for differentiation with respect to a. So differentiate this formula with respect to a using Leibniz rule. We get f dash of a is equals to 1 divided by 2 pi I into integral over c f of z into dou divided by dou a times of 1 divided by z minus a into dz. That is nothing but 1 divided by 2 pi I into integral over c f of z into, on differentiation of this function I get minus 1 into z minus a to the power minus 2 into minus 1, retain dz as it is. On simplification we get 1 can be written as 1 factorial divided by 2 pi I integral over c f of z minus 1 into minus 1 is plus 1, z minus a to the power minus 2 is taken to the denominator, that is z minus a whole square into dz. Again apply the Leibniz rule to above equation. We get f double dash of a is equals to 1 divided by 2 pi I into integral over c f of z into dou by dou a times of 1 divided by z minus a whole square into dz. So on differentiation we get 1 divided by 2 pi I integral over c f of z minus 2 into z minus a to the power minus 3 into minus 1 into dz. So that is nothing but minus 2 into minus 1 is plus 2. So I taken outside and write it as 2 factorial divided by 2 pi I integral over c. Remaining is f of z, and z minus a to the power minus 3 is taken to denominator, z minus 3 whole cube into dz. Continuing this way, after differentiating n times, we get fn of a is equals to n factorial divided by 2 pi I integral over c f of z divided by z minus a to the power n plus 1 into dz. Next one, Cauchy's inequality. If f of z is analytic inside and on the circle capital C with center z equals a and radius r, then a modulus of fn of a is less than or equals to capital M into n factorial divided by r to the power n, where n is 0, 1, 2, 3 and so on, where capital M is a positive integer such that mod f of z is less than or equals to capital M for all z on capital C. That is nothing but f of z is a bounded function and bounded by capital M. Now come to the proof of the Cauchy's inequality. We know that a general Cauchy's integral formula, that is fn of a is equals to n factorial divided by 2 pi I integral over c f of z whole divided by z minus a to the power n plus 1 into dz. Apply modulus on both sides, we get mod fn of a is equals to mod n factorial divided by 2 pi I integral over c f of z z minus a to the power n plus 1 into dz. Apply the modulus to each function, we get mod n factorial divided by 2 pi mod 2 pi I integral over c mod f of z divided by mod z minus a to the power n plus 1 into mod dz. We know that mod f of z is less than or equals to m, hence our equation implies is less than or equals to mod n factorial is n factorial, mod 2 pi I is 2 pi because mod I is 1 integral over c, mod f of z is m, mod z minus a to the power n plus 1 is mod z minus a to the power n plus 1 into mod dz, which is less than or equals to n factorial divided by 2 pi I integral over c capital M divided by r to the power n plus 1, because mod z minus a is r into mod dz, hence which is less than or equals to n factorial divided by 2 pi into capital M divided by r to the power n plus 1, because these are all independent of z. So hence integral over c mod dz left in integral. But mod z minus a equals r, which implies that z minus a equals r times of e power I theta, which implies that z equals a plus r into e power I theta. Hence dz equals r I e power I theta into d theta. Then mod dz equals r into d theta, because theta is always a positive, and I mod I e power I theta value is 1. Hence mod fn of a is less than or equals to n factorial divided by 2 pi into capital M divided by r to the power n plus 1. Our integral changes, integral from 0 to 2 pi r into d theta, which implies, which is less than or equals to n factorial divided by 2 pi into capital M divided by r to the power n into theta from 0 to 2 pi, because r is taken to denominator n plus 1 become n. So remaining only 1 into d theta. So integral value we get theta. So which implies that which is less than or equals to n factorial divided by 2 pi I into capital M divided by r to the power n into 2 pi, which implies that mod fn of a is less than or equals to capital M into n factorial divided by r to the power n, because 2 pi get cancelled. Hence the proof. And final, that is Liouville's theorem. This statement of Liouville's theorem is, if the f of z is analytic and bounded in the entire complex plane, then f of z is constant. F of z is analytic and bounded in entire complex plane, then f of z is constant. So proof is very simple. From the Cauchy's inequality, we have mod fn of a is less than or equals to capital M into n factorial divided by r to the power n, which implies that mod f dash of a is less than or equals to capital M into 1 divided by r. That means I taken only a first derivative. For the entire complex plane, radius r is very high. So if we consider entire complex plane, radius is very high. That means it tends to infinity. Hence, capital M divided by r is tends to 0. Thus, mod f dash of a is less than or equals to 0, which implies that f dash of a equals 0 because modulus value is non-negative. Hence the only possible value is f dash of a equals 0. Since a is any arbitrary point, f dash of z equals 0 for all z. Therefore, f of z is constant. This completes the theorem. Thank you.